This is the third and the last video for verifying eigenvalues and eigenvectors for a 3x3 matrix. We have here matrix A and sets of pairs of lambda values and vectors here, and we are going to verify if each pair is an eigenvalue and eigenvector of the 3x3 matrix. To do that, we are going to satisfy this process here. When we multiply our matrix with a certain vector, depending on which vector we're going to work later, can be represented or can be rewritten as the product of the corresponding lambda value times the same vector. If we could do this, then that means the lambda value is the eigenvalue and the vector is the eigenvector of this given matrix. So let's start with this one here. We have A times the first vector must be equal to the product of your first lambda value times the same vector. So our A here is 4, negative 1, 3, 0, 2, 1, sorry. Okay. Let's do it again. 0, 0, 3. To be multiplied with our first vector, we have 1, 0, and 0. After the result of this, let's see if we could actually rewrite this as well as the product of your lambda, the same lambda or the corresponding lambda times the same vector. And if we could do that, then the pair of lambda value is and the vector is a pair of eigenvalue and eigenvector of matrix A. Don't forget that this is a 3x3 matrix to be multiplied by 3 by 1. So by concept, the result should also be 3 by 1. Let's do it step by step. 4 times 1 is 4. This is 0. That's 0 as well. So you have here 4. Next, 0 times 1 is 0. 0. 0. So you have here is 0. And finally, 0 times 1 is also 0, 0, 0. So this is even shorter because we have presence of multiple zeros in our matrix, and including in our corresponding vector used. So if we are going to take out lambda sub 1, which is 4, the resulting matrix here is 1, 0, 0, which corresponds to your assigned vector here. This means, again, this is our lambda sub 1. 4 is the eigenvalue with the corresponding 1, 0, 0 as the eigenvector of your matrix A. That's just one. Okay? And we are still going to verify the next two pairs. So let's replicate this for our second pair. So you have A times vector x sub 2 must be equal to your lambda sub 2 times your second vector. A, the same. So you have 4, negative 1, 3, 0, 2, 1, 0, 0, 3. To be multiplied with 1, 2, 0. Again, the idea is for this to be matched. Okay? So you have the result here, still 3 by 1. 4 times 1 is 4. 2 times, 1 times, negative 1 times 2 is negative 2. 4, negative 2, oh, that's, of course, this is 3, 0. So 4, negative 2 is positive 2. Next, 0 times 1 is 0. 2 times 2 is 4. 1 times 0 is 0. So you have here 4. And then 0 times 0, that's 0. 1. 0 times 2 is also 0. This is 0 here as well. Since our lambda is 2, take out that 2. We have here 1, 2, and 0. And noticeably, this is our lambda sub 2. This is actually our same second vector. This means that lambda sub 2, which is 2, is your eigenvalue with the corresponding x sub 2 as our eigenvector of the same matrix. And let's finish this with our last set So you have your A. Let's make it thicker. 3 must be equal to lambda sub 3 times the same vector sub 3. Our matrix is still, you can see it here, this one here. 4, negative 1, 3, 0, 2, 1, 0, 0, 3 to be multiplied with your third vector, which is this, negative 2, 1, and 1. So you have negative 2, 1, and 1. Again, this should reach an expression equal to the product of your lambda sub 3 and your third vector. Let's take note of our lambda sub 3, which is a 3. Okay, this is our 3. Okay, let's do it like this. The resulting matrix is still 3 by 1. 4 times negative 2 is negative 8. 1 times, negative 1 times 1 is negative 1. So negative 8, negative 1, that's negative 9. 3 and 1 is positive 3. Negative 9, and then plus 3, negative 6. Next, 0 times negative 2 is 0. 2 times 1 is 2. 1 times 1 is 1. 2 plus 1, 3. Finally, that's 0. 0. 3 times 1 is also 3. Take note, our third vector is 3. Again, I have it here, but I just placed it here earlier. When we factor out 3, negative 6 will become negative 2. 3 will become 1. 3 will become 1. And this is again our lambda sub 3. And this, same thing here, or if you would like to, again it's here. That's our third vector. This means that the value of lambda, which is a 3, is the eigenvalue together with its eigenvector of negative 2, 1, and 1 for the given matrix A. So this is how we satisfy, or verify rather, whether the pair of lambda and the vector is an eigenvalue and eigenvector respectively for a given 3 by 3 matrix. This, first and foremost, should be satisfied. So this is for this video, and thank you very much for watching.